Thank you very much for the introduction. Okay, so I'd like to thank the organizers for this very timely invitation so that I could escape the heat, hot heat Japan. I'm really enjoying this. It's very nice, yeah. It's dry and cold. Temperature is nice. Okay, so in any case, the title I include the KP Soliton, and many people think I'm still doing KP Soliton, yeah, but something interesting. Oh. Okay, so the next page. All right, so this is based on the just archived paper. So non-crossing permutations for the KP Soliton and the Gelfand-Dickey reductions, and maybe vertex operator part. I think I don't have time to explain. But here's okay, so two words, the non-crossing permutations and Gelfand-Dickey. Those are maybe some of them you're familiar, but probably not. Okay, so KP equation has many solitons, but particularly one soliton solution is given by this form. Okay? So this one, I just emphasize there are two parameters, kappa, kappa j. I put some order. And then the argument theta is, let's say, P1x plus P2y plus P3t. Then P1, P2, P3 satisfy so-called the soliton dispersion relation or some linear dispersion relation. And that really makes the game here. Okay? So you just remember, P1 is the difference between two parameters. P2 is just a square difference, and P3 is a cubic difference. And that's all, right? Okay, so that's one is just a comment. So P1, P2, P3 satisfies the linear dispersion relation. So you have the three the real numbers, right? There's one constraint, and this is a general solution. So if you prepare two parameters, you can actually parameterize the surface. Okay? And that's all about. All right, then I said Gelfand L reductions. This L is just a number, some L is taking 2 and 3 and so on. So L reduction usually the people refer du dTL equals 0. So U does not depend on TL, right? Then now if you go back to the soliton solution, now you know the T2, for example, 2 reduction, meaning is this must be 0, right? 3 reduction, meaning this must be 0, right? And it turns out you get a very nice algebraic curve, right? So this is kappa 1, kappa 2, kappa 1, kappa 2, some relations, and that gives you the quite nice algebraic curves. Okay, so anyway, so this is a skip, and here, so let's start doing some example. So first example is KdV, the 2 reduction. That means du dy or du dt equals 0, then kappa 1 squared minus kappa 2 squared 0, right? So then kappa 1 is plus minus kappa 2, and kappa 1 equal kappa 2, of course, is just a 0. So you take kappa 1 is minus kappa 2. So there's a kappa 1, then reflection is here. So actually, you do have the curve, right? So this curve, I call the spectral curve, and this is most important here. Okay? So 2 reduction associated with this curve. This is just parabola. Okay? You take alpha constant, then you take 2 roots, and that is kappa 1 and minus kappa 2, right? Okay, so this is this is another thing so I'm going to describe. How to get the n-soliton solution. It just takes the n pair of the kappas, right? So that means you take alpha, they take another alpha, then you just get all the different kappas, right? And now the soliton packing, you can do many alphas here, and you have a band here, right? And then you get the genus 1 stuff, right? So that's also included here. Okay, so next one is actually saying Boussinesq. All right, so this is the 3 reductions. They are not T3. So you have a kappa 1 cube minus kappa 2 cube equals 0. But this solution is actually complex. So it's not really good because I'm dealing with a real, regular soliton solution. So if you do actually ask the 3 reduction, there is no such soliton solution. Here, I mean the soliton is here. The U go to 0 at the boundary. So X goes to infinity, U go to 0. And such kind of solution does not exist in Boussinesq because this is not a correct form. You have to do some boosts, right? Okay, and also Okay, so this is the one I'm telling you algebraic curve here. Kappa 1 square plus kappa 2 square plus kappa 1 kappa 2, which is 0 is a trivial. Okay? So if you have this with some positive constant, then this is actually ellipse. Right? So genus 0 ellipse appear in here from here. And that's the all things you are going to see. Okay, so now what you do is this called the Basel deformation, some of the singularity theory. So kappa cube equal alpha is so degenerate. Then you do some Basel deformation by putting C, right? Then C is positive, you have 3 real roots, right? So then, okay, this C is actually appear in this way. So the T term is kappa 1 cube minus kappa 2 cube. The C times kappa 1 minus kappa 2. So kappa minus kappa appear, the X plus CT. So this is suggesting you just use new coordinate C, then you have this standard, the Boussinesq. And this is the good Boussinesq, right? And the good Boussinesq is so bad in the physical application. And that's really not physical. Okay? And you see why. Okay? Yeah, good is bad. Bad is actually good. Okay, so let's go. Okay, so this is the cubic curve, and then you take alpha. There are 3 different types of solution, and the one Soliton solution you can get. So one is you take 2 roots, kappa 1, kappa 2, then you get this condition. So V actually gives you the velocity, right? Kappa I plus kappa J gives the velocity. So 1, 2 point, then you get that velocity is minus 1/2 C0 to C0. Right? C0 is just a constant appearing in the equation. Yeah, this is C0. This is hyperbolic part, C0. Okay, so then amplitude is 0 to some limiting. And this is also interesting. The good Boussinesq, you cannot have huge solid. It's limited because the ellipse, there are some limitation. All right, so then you take the root is kappa 1, kappa 3, then you have this range. Right? And this is, okay, including 0 velocity, but amplitude is not 0. So there is a soliton which stays in the middle and finite amplitude. And that's not physical, right? There's no such the water wave, sitting soliton, no moving. But anyway, so good Boussinesq has this solution. Okay, and the last choice is here. Kappa 2, kappa 3, you get this ring. Okay? So there are the 3 distinct velocity region. And the amplitude is just the y is the same as this one, and the other one, the middle big one, has a very slow speed. So in the KdV, you remember the high speed soliton has the peak is high, amplitude is high, but this one is not. It's opposite. Slow one is higher. Okay, so then let's go. Okay, so now the one more remark is I was talking about only one Soliton solution, but there is another type of the Soliton solution for Boussinesq, and this is called resonance. So resonance, the Soliton solution, it means, okay, so this is T2 direction, this is X, right? So there are 2 Soliton, one, okay, so this is kappa 1, kappa 2, kappa 2, kappa 3, and they actually merge to create the bigger 1, 3 Soliton. Right? And this is opposite. Okay, so this is a fusion. This is another fission also appear. It's a time symmetry. So you can always assume one you have, other one you have. But in the algebraic term, it's different Grassmannian. Okay? And that's also you will see. Okay, now the question. What is the general Soliton solution of the good Boussinesq? And I asked several people, and they think they know everything about the Qi&pi and so on. But it's not really true. Right? So, okay, for example, like here, this is a Y soliton, right? So once you have one, you may have another one and just combine. So you may have 2 Y, right? But impossible. If you have 2 Ys, it becomes very singular. Okay? So at most 1 resonant solution and bunch of the usual soliton. Okay? And that is the structure of the good Boussinesq. Okay, so anyway, you will see. Okay, so now this is a bit boring. And if you read my book, then you don't need, you can skip here. Okay. Now I have to advertise, right? Okay, so anyway, so the Qi&pi soliton is in science is very simple. So you just write down U is in terms of tau function, right? And you prepare the arbitrary n number of f function, and f satisfies the linear PDE, right? And just solve. So you can do this one by the Fourier series or something, Fourier transform or something. You can do it, right? Then put f1 to fn, those are fundamental set of solutions, and put in the Wronskian form, right? So this is Wronskian with respect to x. So f1 prime, f1 to n minus 1, and put it in the determinant form, and that gives you the Soliton solution, right? And that's it. So you can create many, okay? But I like to restrict the solution in the solitons, right? So solitons, what I mean is here. So KP soliton, you take a finite dimensional solution. That means here. So EJ is a fundamental solution of this linear system, right? So Tn derivative, just nth derivative of x. So that's why you have this structure. So T1 is kappa 1 to kappa j to 1 power, T2 is kappa to 2 power, and so on. So this is a very trivial solution. I put it in here, I take a linear combination, right? And that's, I call the Soliton solution. And kappa is now order. And this order is very important. Okay? When you talk about the regularity or some positivity, you need the order. Okay? If you change the order, of course, change the sign in the determinant, right? Okay, anyway, so this is, okay, so one factor is kappa, and the parameter is A. This is n by m matrix of full rank, and that is here, right? So the classification of KP soliton is nothing but the classification of this matrix. And this is the usual n by m. And many people stop here, okay? I have a general solution and done, right? But if you ask more, the regularity, then there are a lot of interesting combinatorics comes in, okay? And that's actually the part. All right, so you can write down the tau function in the product of two matrix, and this is n by m, and this is the m by n, and then you do Binet-Cauchy expansion. Then you take, say, I1 to In columns, take a determinant, multiply by corresponding row in the row, the rows marked by the I1 to In. Then you just make all possible combinations. Oh, this is out. Battery is out. So, okay, anyway, all possible combination, you get it? So now the ordering actually tells you. So this part is always positive, I tell you later. And then if the coefficient has to be positive or 0. Okay? And that's the next slide, I think. Here. Oh, and also this is the minor, yeah. Okay, so now this I1 to In part, you can put into this way. Then ordering actually implies the Wronskian part of the exponential function becomes positive. So now the theorem saying that tau is positive if and only if the O's coefficient has to be non-negative. And of course, if this is true, then this way is easy. This is just by definition. But tau positive implies this one is not easy. So you have to do a lot of stuff. All right, then this actually defines the A is an element of so-called totally non-negative Grassmannian. Yeah? But that's it, yeah. So that is a crash course of the KP solitons. Yeah. Okay, now the other ingredient I like to tell you is, okay, so you take A, and the irreducible meaning is you cannot reduce number n, number m, right? So some of them is just trivially just the one column is one row has only one non-zero, then you can always remove, and you can reduce the Grassmannian, right? So anyway, so irreducibility is not really. Okay, then let's I1 to In is a pivot, and J1 to Jn minus n is a non-pivot, right? And then Y positive, I'm talking about the soliton graph, right? So asymptotic, Y goes very large positive, then you observe n solitons. This n is the same as this size n, okay? And then this is the I, and the permutation pi exists. The image is always bigger than ik. Okay. So this bracket, I make order always. Ik and pi ik is the pi ik is bigger. So this is called exceedance. Right? So this is the index actually increase, and the non-pivot one is always decrease. Okay? So image of JL is smaller, and this is a minus n. And the picture is like this. So inside there are a lot of interactions, and the interactions actually consist of X and trivalent, and those things disappear. Okay, so this is a picture, just remember, right? Okay, now the remark is anyway. So irreducibility, reducible means you have a derangement, then you have some decomposition. And one more ingredient I like to tell you is called permutation diagram, or sometimes called code diagram. Right? So in the upstairs of the code, like showing ik goes here, and the one goes to some. Right? And the bottom part is actually the non-pivot, the indices. Right? So that's the picture, just remember. All right, then this proposition is very nice and very simple. Right? So what this is telling you is, okay, let's go to the example. So example saying 4716235. Okay, so this means 1 goes to 3, 2 goes to 7, 3 goes to 1, and 4 goes to 6, and so on. Right? So this is 1 go to 4, 2 go to 7, and 3 go to 1, and 4 go to 6, and 5 go to 2, 7 go to 5. Right? Okay, you got it, right? Okay, so from this picture, you can actually decide how many parameters you can have in the A matrix, right? So this is the proposition. So proposition saying is dimension x pi, the meaning is the number of free parameter inside of the A matrix. So this is saying pivot, number of pivots, and number of crossings in the here is a red mark, and number of cusps in the lower part is just the green one. So just count 1, 2, 3, 4, 5, 6, 7, 8. So this is a dimension is 8. Okay. In the generic situation, you have this picture. Right? So you have a 1, 2, 9, 11. Yeah, 11 the possible free parameters, and that is usually called the top cell. They're marked by this permutation, but this one is actually co-dimension actually 3. So there's 3 constraints. Actually, you get to this picture. Right? And how to construct this A matrix all written in my book. So if you're interested, you just buy. All right. Okay, now question how to choose those kappa and A, right? And for the general direction. All right, so in the general principle is here. So general principle saying kappa L equals alpha. That's the starting point. Okay? So I have the kappa J L minus kappa J to the L, and this part has to be 0. But that one is the else roots of unity. So that's all complex roots. So you like to have the real roots. And then what you do is a deformation parameter, Cj, right? They put in Cj and then L distinct roots. Okay? And just put it in here. Now you have L distinct roots. Okay, so like this one. So this one is 1, 2, 3, 4, 5, 6, 7. Okay? So this is L equals 7. Then you take alpha 1, alpha 2, alpha 3, and so on. Okay? And then you gather all this stuff. Oh, maybe I don't have time, so I'll explain the detail. Okay. So the idea is that so you have a curve, then you just take the one constant and puts all the roots. Right? And that is the source of the kappa parameter in the Soliton solution. Right? Okay, then you have now each nk, mk. So each one meaning is you fix alpha k. So one alpha k, you have nk, mk, and then takes the positive. And then you are guaranteed. And also the one more important thing is if the matrix A is not totally non-negative, you cannot associate the permutation. So if the totally non-negative element, you can always associate the uniquely the one permutation. So this is needed, and then you get here. Now I combine several alpha k's, then you have several different kappas, right? And then you have a different A matrix. So I defined K direct sum of the matrix, and this one is actually sorted according to the order of kappa. Right? So one line you have kappa 1, kappa 2, kappa 3, for example. Then you put the other one, then kappa 1, kappa 2, kappa 3, kappa 1. You have now different weights, right? Then you have to assign this matrix. Right? So this one is normally not totally non-negative. Okay? So if you put this one and calculate kappa 1 to kappa m, then put it in the tau function, most likely you get a singular solution. So now how we get the regular solution? And that's the point. Right? So that's the conclusion here. Okay, so that's maybe okay. So say what I'm saying. So usually if you do just the kappa direct sum of the matrices is not TMA, totally non-negative. Right? But say what I'm saying, the mutually crossing. So this is another keyword. If the code diagram or permutation diagram is not crossing, then this guarantee that you do have TNN by changing the non-zero constant or free parameters in each A alpha K, right? So that's our thing. So this saying, yeah. All right, yeah, by adjusting the sign, only sign in the non-zero element in each A alpha K, so that this is okay. So left-hand side is the totally non-negative one, the created by this arrangement of kappa, and the permutation. It turns out just a product of all the permutations. Okay? So you have two permutation. Just okay. Product meaning is this is okay. Anyway, so anyway, product of the permutation is just the cyclic notation of the permutation, right? Cyclic one, you can multiply. Okay, so then you have next one. Okay, let's go with the example. So example KdV is no problem because you take alpha 1, alpha, so on, and each the permutation diagram is just from here to here, from here to here, from here to here, no crossing, right? And if you put in this matrix, 1, 2 matrix, each one is just a 2 kappas, right? So you have the 1, 2, the element, then put everything in the kappa direct sum, then you get this one, right? But in the beginning, it's A1, A2, AN are all positive. But this matrix is not totally non-negative. So what you do is you just adjust the sign here. Okay, then you can get this. Okay? And this is totally non-negative. Okay, so this what you do is here. Right? So you have 1 cause, 2 cause, and n cause here, as they are not crossing, then you can automatically get. And the y direction, there are no y in the KdV, and they are here. And everything propagate in the left direction. Right? And this is our picture. Okay, now go to Boussinesq. So Boussinesq, you have a cubic curve. So you have here, right? There are 3 different choices. So A alpha could be 1, 3, 1 AYS. So you take all 3 points, or you take 2, 3, all 3 points, but you have F1, F2, 2. Right? And then you get those code diagrams. So all right, now the question is, you have all the basic, the permutation, you just start combining. Right? And only the ingredient is just don't cross it. So just put in all the things inside. Then, right? So, like I said, example. So you start from here. The alpha 1, you take 3, then alpha 2, put in 2. Then this one, right? And put this one is inside here. Right? So if you take the alpha 2 roots, this guy and this guy, right? Then they will cross. Then once you cross, it's not totally non-negative. And proof is actually so simple. So proof is coming from once you cross the chord, you increase the dimension. Remember? At the very beginning, I said proposition is you have a chord and you have a crossing, you have a dimension. Right? That means you need more free parameters, and that's impossible. Right? And that's it. So then K direct sum, and you have this one, you get all the Grassmannian 2.5. Right? Okay, so I think the next slide. Oh, yeah. So this is general case. So Boussinesq case, there are only 4 different cases. One is the resonance solution, then bunch of line soliton propagating left and propagating right. And this is another one. This is the fusion. This is a fission. And this is a large one soliton appear. Then this is it.
that's already at most one resonance solution. Right? Okay, so maybe that's the last one. Anyway, so if you do the soliton, the gas, so what you do is actually you put the random kappas here, right? And you remember this is a curve that's coming from this one, right? So if you take alpha to alpha k, so many lines, right? Then you can see kappa is restricted here. Right? For example, alpha and alpha k, you have this range, and this one is packed by the solitons. Yeah, and that may go to the cut. That I don't know. That's a possibility. All right, so that's all the stories, and then I think, yeah, this is all the pictures. I saw the last night the poster session, and somebody talking about this one. Yeah, so that's the same story, and each point here. So, for example, BB, the blue line, blue soliton interaction. This must be positive, the phase shift, and blue green line is a negative phase shift, and so on. This is all you can actually manage, because of this diagram. Okay? So, okay, so one more information. So if the soliton this one interact with this one, is always the positive, the phase shift. And this one interact with this one is called the what? The alignment, and then this is always negative, the phase shift. Right? So this nesting is always the positive, and the alignment is always negative. That's all you can see, or you can calculate explicitly. Okay, so this is the last one. So this is actually one I really like to do, a two-dimensional soliton gas. So what you are seeing is, okay, this is, by the way, done by the Abenda Grinevich about the KP soliton. And left side picture is put the theta function and produce the quasi-periodic solution, and this is it. Okay? And then the curve, which is not hyperelliptic, by the way, this place, but it's a reducible. Okay, meaning it's anyway. So there are some small parameter epsilon here. Right? So the left A picture is epsilon is not so small. Then you take a small, then you pinch all together, then you get the KP soliton. But here, it's not only KP soliton. There are a lot, I mean, there are many KP solitons, but not just one, right? One type, because of this is a quasi-periodic. So this means actually you have a flag, not a Grassmannian. Okay? So Grassmannian consists of many, flag consists of many Grassmannian, and each Grassmannian has KP soliton. So all the KP soliton mixture, then you get this picture, right? So now you can see. So what is the permutation here? What is the permutation here? What is the permutation here, and so on, right? Okay, so now the ultimate goal is you consider random permutations, right? Then you have a lot of nice weights, like a Shor weight or there are a lot of the weight you can measure. You can put it in this permutation ensembles. Then you calculate certain things, and what I like to know is what is the most likely pattern appearing in this picture. Okay? So you just calculate some ensembles, and you take the random permutations, and what is the most likely permutation, which means what is the most likely the picture you observe. Okay, okay, I think that's all.
I mean, when you do this three reduction, and then you keep non-crossing, then that reduce the cuts and number. So what's the maximum number you can have? Like, but for example, like you might have all the regular solution solution for the P, then like a sample of them like into LV, different LV.
Yeah. So the point is, so if it's a reduction, there's all the kappa parameter is restricted.
Correct.
So there's a cubic cut. So you can take at most 3 points. You can take 4 points. It's outside of the cut. So 3 points and 3 points and all 3 points. But you cannot take 3 point and 3 point. Then you get crossing because of this side. Then you get automatically the singular solution. So this is the condition. What I said is non-crossing is if and only for the regular solution.
Okay. That's good from account.
Yeah. So the other point is you can get many line solitons.
Right.
But because of the curve here, you can take all the things and take pairs. You can take many line solitons, but in this case, we have only one resonant solution. Okay. So, and also the pole reduction, you have one huge one, resonant 2,4, and that's only one resistance. And once you take this one, only the line soliton you can combine. So there is Combinatorics problem.
When you speak about permutation, so I understand which permutation is signed in such a fine market.
Yeah, exactly.
Say which is the duration, but I mean, permutation are very well here. So if you are
Okay, so here, this is a certain classification. Then you take a simple fix, then you can always see unique permutation. But inside, you don't know. There's a lot of interaction. Simple fix, we have those like Soliton, and those actually change one index. So 3 to 5, some. Then you go around, then you get the permutation. So A matrix, you can get unique permutation. So you have different A matrix, different asymptotics. But now so this picture, the periodic, which means just not only one Grassmannian, there are many Grassmannian here. And then you do some other something. Yeah, okay, so this is just the what. I couldn't really do anything out of this statement. So you're welcome to do something here, but don't think it's easy. The phase shift part is maybe somebody is doing already, and maybe for reduction, type reduction, you can do it, but in the user treatment. So I don't know, formulation is very fine. Yeah, permutation, metal permutation, the measure, you can solve it. So it's totally combinatorial problem.
the phase shift equal to 0 in some cases.
Very second.
Are there two solitron solutions with 0 phase shift? Just perfect for all.
Oh, no.
Can
KP.
Huh?
Well,
Okay.
KP, there are 3 type of the asymptotic cassette. Okay? So either this one is nesting or alignment. And there is no zero phase shift.
Never.
Yeah, and also other one is like a trivalent, so you don't really calculate it. So there are no because this is the exponential summation. I think that's maybe the reason. If it's the algebraic one, then no phase shift. Then better be all nonsense.
Okay, so I think we can thank you again.